Hello there and welcome. Ever just stopped and wondered how the lights stay on? I mean, not just in your house, but across an entire country all at once. Well, it's not magic, it's engineering. And today we're diving into the absolute bedrock of that engineering, power system studies. These are the tools engineers use every single day to design, manage, and, crucially, protect our electrical grid.
And I mean, just think about that question for a second. A national grid isn't just a bunch of wires. It is, without a doubt, one of the most complex, interconnected machines humanity has ever built. It needs to be balanced constantly, you've got to predict what's going to happen, and you have to protect it, all in real time. This sheer scale presents a monumental engineering challenge, and that's what we're going to unpack.
So, here's our plan for today. First, we'll look at the grand challenge of just keeping the lights on. Then we'll open up the engineer's analytical toolkit. We'll see how they map the system's normal flow, and then, what happens when things go wrong? We'll also cover the clever universal language they use to make the maths manageable, and finally, we'll see how all of this makes engineers the true architects of the grid. Right, let's get started. Before we can really get into the solutions, we need to appreciate the sheer scale of the problem that engineers are up against every single day. You know, the power you're using right now was probably generated hundreds of miles away, but it got to you instantly and with incredible reliability. That stability is absolutely not an accident. It's the result of nonstop, rigorous analysis, making sure the system can handle every single flick of a switch and any potential problem. This, right here, is the core reason power system studies even exist.
So, how on earth do engineers deal with all this complexity? While they certainly don't guess, they use a powerful set of tools called power system analysis, which is basically a specialized kit for diagnosing and designing the entire electrical grid.
Think of this list as a menu of health checks for the grid. Each one of these studies looks at the system through a completely different lens. Now, while they're all important, today we're going to focus on the two most fundamental ones: load flow, for understanding how the system behaves normally, and fault current, for figuring out what happens when something breaks. Okay, let's dive into that first major tool. Look, to understand any complex system, you first have to know what its normal looks like. For the grid, this means mapping its day-to-day operation, checking its vital signs, if you will. And that is done using a foundational analysis called a load flow study. What this really means is that a load flow study is like taking a snapshot of a perfectly balanced, smoothly running power system. It's a calculation of all the voltages and all the power flows across the entire network, assuming everything is ticking along just as it should be. It really is the starting point for almost any power system analysis. This quote really gets to the heart of it. The study answers a pretty simple but absolutely vital question. If we know how much power is being generated, and we know how much everyone is trying to use, where exactly is all that electricity going? How is it flowing through all the different lines and transformers to get there? And this isn't just some theoretical exercise, the results are critical. A load flow study tells engineers if any cables or transformers are in danger of overheating. It tells them how much energy is just being lost as heat in the lines. It lets them assess if the system can survive an unexpected outage, and it tells them if they need to add equipment to keep the voltage stable. It's incredibly practical. But of course, a grid that's only designed for a perfect day is a pretty fragile one. Engineers have to spend a huge amount of time preparing for when things go wrong. And that brings us to our next critical tool, the fault study, which is all about analyzing the grid under stress. So a fault is really just another name for a short circuit. It could be a tree falling on a power line, a bit of equipment failing, or a lightning strike. When that happens, a truly enormous amount of current, we're talking many, many times the normal level, rushes towards that fault. Understanding just how big that current is absolutely critical for safety and to stop things from, well, blowing up. And here is exactly why that calculation is so vital. The results of a fault study directly influence the design of the grid's safety systems. Engineers use it to pick out circuit breakers that are strong enough to interrupt those immense currents. It helps them make sure that expensive gear like generators and transformers won't burn out. And it tells them how to set up the protective relays that detect a fault and isolate it in milliseconds. Now, here's something really important to understand. A circuit breaker, the big switch that protects a circuit, actually has two different readings. Its break duty is the fault current it can safely interrupt when it's opening. But its make duty is the much higher peak current it has to survive if it happens to close onto a fault that's already there. And as you can see from the table, that make rating can be up to 2.5 times higher, That's a huge difference. A fault current also isn't just one single steady number. It's actually at its absolute highest in the very first milliseconds. That's the subtransient state. Then it quickly decays through the transient state until it settles at a lower sustained level. Engineers have to analyze this whole sequence to make sure their protection systems are fast enough to catch the worst of it. So, trying to analyze a network with thousands of components running at dozens of different voltages sounds like a complete mathematical nightmare, right? Well, to get around this, engineers came up with a brilliantly simple system that creates a kind of universal language for the entire grid. It's called the per unit or PU system. The easiest way to think about it is like using percentages. So instead of dealing with thousands of different values for volts, amps, and ohms, every single value is just expressed as a fraction of a common base value. So a voltage of 1.0 per unit is just normal, and 1.02 per unit is simply 2% above normal. This simple trick makes comparing things across the entire grid vastly simpler. And the benefits of this are just huge. It means an engineer can look at a number and instantly know if it's normal or abnormal, no matter where it is in the network. It massively simplifies the equations by getting rid of fiddly numbers like the square root of 3. And best of all, it elegantly handles the changing voltages across transformers, which are usually a real headache. It just turns a mess of numbers into a clear, manageable model. Okay, so let's pull all the ideas together and see how they empower engineers to become the true architects of our power grid. Ultimately, things like load flow, fault studies, and the per-unit system aren't just topics in a textbook. They're the fundamental design and operational tools that are used every single day. They're what allow engineers to act as the architects and the guardians of our power grid, making the big decisions that guarantee the power we rely on is safe, reliable, and efficient. And that brings us to one final, forward-looking question. Our grid is changing faster than ever before. We're adding unpredictable renewables like wind and solar, and new demands like charging millions of electric vehicles. So how do these foundational studies need to evolve to manage the much more dynamic and complex grid of tomorrow? Well, that's the challenge for the next generation of power system engineers. Thanks for joining me for this explainer.